Okay, we start up again. Continuing with our problem, we could not use a simple foam. It was a steady state solver. We need a transient one. So what should we do? Well, let's see now. I think I have here the first one we looked at, the cavity case. I think even it's stripped down. Well, almost. Well, never mind. I will use the cavity case because in that one, that was a transient laminar simulation with icofoam. So I want to use that one. But now with my new geometry. So how do we do that? Copy -R, the cavity case. And then I give him a new name. I call this one VKV. Now you know why I called it VKV. It stands for von Karman vortices. But I have that folder already. Let's call him icofoam. Or yeah, whatever, icofoam. Then I have copied everything from the cavity into that folder. And let's go there. Here. Well, obviously I have been simulating this one previously, so let's clean it up. Foam clean tutorials, like that. And I had some small files here. Let's get rid of those as well. Something like that. Now the case should be totally clean. For this cavity case, and yeah, you remember we had a moving top wall and else everything was then squared, so we have to clean it up a little bit. First of all, inside this zero folder, yes, we have pressure and velocity, but I have my own for my case. So here I can now crudely remove this zero folder, and then I just copy it from this VKV case that we had. So I just copy, I need -R here, it's a folder. Copy that one into where I'm standing. So now I have my new, no, that was wrong. Cannot cp -R, no such file or directory. I'm missing a period. It should be a double dot. Now we have it. So now I have my new zero folder in the geometry that I have. Same go with the block mesh dict file. I can copy that one as well. That's just a simple file. VKV system block mesh dict, and put that one in my system folder. He will then overwrite my block mesh dict. So now that one should be correct. What about the rest of the files? Well, we better check them out. Let's see, first I can kill this one. And then gedit. What should we do first? Here, let's look at the constant folder. Here I only have one file, transport properties. That was the viscosity. Here's 1/100. That's beautiful. What else do we need to change? The zero folder should now be okay. I had some additional files here. I should remove them. Never mind. The control dict. This was a setup for the cavity case. But now I have a totally different case, so I have no idea what we should have here. We can start from 0, but probably half a second. That's way too low. Let's go to, what should we say here? 400 seconds. Delta T, how big can he be? Well, I have no idea. 0.5, why not? right interval 20. Yeah, okay. Yeah, try that one. Just to clean up the case here a little bit, I had some additional files in my system folder. I don't know what they are even, so let's get rid of them. Remove system, and this block mesh dict, and also this decompose. I'm not using that one. Now my system folder is nice and clean. Let's try this one. Block mesh and check mesh. No errors. Then we try to simulate ICO foam. Yeah, it didn't crash. Went all the way to 400, but this one I don't like. What's this? The Courant number. What was the Courant number? Well, that is sort of the distance for your local velocity multiplied with your delta t divided by the local delta x or delta y or delta z. You're not allowed to travel longer than one cell length during one time step. This should be smaller than 1. So I had a little bit too big delta t. How many result folders did we get? We got some. Let's clean it up. Foam list times minus remove. Foam list, thank you. Something like that. And then I have to reduce my time here a little bit. 25, why not? And we try again. I haven't changed the mesh, so we can just simulate. And yeah, much better. 0.6, beautiful. Let's have a look at the solution. Para foam. And we apply, and we look at, say, the velocity. And then we play. And then nothing seems to be happening, does it? How come? Nothing seems to be happening. We should get this nice vortex shedding. Why don't we? What about the pressure? If you look at that one from the beginning, no, it doesn't change. It doesn't change. What's going on here? Why don't we get this alternating vortex shedding like we should? We have the correct Reynolds number, should be 100 now, but no, he doesn't want to do it. We have some tricks. The page that I showed you here, to obtain this vortex shedding, you should have a Reynolds number in this range to have a nice laminar structure. We have a Reynolds number of 100. Maybe it's too low since I just have a straight plate. So that could be one way to do it. Where do we have it? Here. So I could just reduce the viscosity. Now I have a Reynolds number of 1000. Well, we can try it, see what happens. I have the same time here, so he will just overwrite all my time folders, so I didn't have to remove them. Okay, now let's have a look. Apply, and then we have the velocity, and then we run. No, still don't get it. Ah, there something is happening. I only went to 400, but we hardly had any oscillations there. Maybe we have to run even further, eh? Okay, let's do that. 400. We can take it all the way to 500 then. Why not? And then we can start from latest time. Latest time. And now let's have a look. Here we go. So now we start getting this vortex shedding. Not so impressive here. If you look at the pressure, sort of see the same. But it took a very, very long time before he sort of triggered, before he started. So here maybe it just oscillates a little bit, not much. So maybe we should help him to get things started. How can we do that? Well, we have an option here. If we look at the initial setup for this case, the 0 folder, and for the velocity. Yes, I have my inlet velocity of 1. So that shouldn't be a problem. And the internal field, just to help him, I put 1 all over the place. What if we do the following? I give him something crazy here, something asymmetric. I give him a positive velocity in the y direction. Totally unphysical, but I don't care. Just to help him finding this asymmetry, because when you look at the Navier-Stokes, this symmetrical solution without the vortex shedding, it is actually a solution to the Navier-Stokes. It's just unstable. But mathematically, it will still be a valid solution. But if somebody kicks the door or makes some noise, a little bit noise, then you will trigger, and then you will have a different solution. Same goes with a flow where the Reynolds number is above the critical. Then it should be turbulent. But the laminar solution is still a solution. It's just unstable. So I mean, they have done experiments actually in pipe flow. They were up to Reynolds number 60,000 or something, and still kept it laminar. But I mean, in the laboratory, if somebody banged the door, that would be enough to trigger the flow, and then it became turbulent. So the laminar solution is still a solution. So maybe sometimes you need he needs a little bit help, a little bit noise. So let's see if this one helps. Save that one, and then we rerun the entire case. Yeah, well, we can just remove all these result folders. Where do we have it? Here, somewhere here. Then we start from scratch, and then ICO foam. Here we go. And now let's have a look. Trigger much more earlier, already at 100 or something. So that's one trick. That's one thing we could do, just to help him find the asymmetry in the problem. Just insert something asymmetric here for the entire domain. That could be a trick. Now, for those of you who took this introductory course last semester, let's see, where are we? Should be here somewhere. We had an exercise there. That was number 8, if I recall correctly. So this was simulation of flow around the cylinder and then compare with the experimental values for the screw hole numbers. So we had a mesh looking something like this. And we will then have a solution looking something like this when you look at here the lift coefficient for the cylinder. It takes a long time before anything starts to happen. But when it first happened, then he should sort of be a stable setup, the laminar range here, so it should be okay. And here we also had the option to speed up this startup period. And it looked something like this. Let's have a look. This is what we had. I had to simulate to 150 seconds before he triggered. But using what I call here a field initialization, you almost start from zero. And how to do that? Well, I have used something called set fields. This is something also we are going to use also later. You can specify sort of an inlet state for the internal fields, but at different locations. So here I just choosing one box and then setting very weird velocities. And physical maybe, but you shouldn't crash for that reason. Unless you choose totally insane numbers, of course. So using this set fields trick, that could actually be a very good idea. Now for the setup that I have here, it looked something like this: symmetry line, outlet, and then a symmetry line. So yes, I just chose the entire domain. But say if you had around the cylinder, what we could have done with this set fields trick, I could choose an area here, for instance, a box, or you could even choose a sphere or whatever you want. And then here set some velocity, maybe in that direction, for this entire area initially. And then I can choose another box and then specify something else. Maybe a velocity. I mean, you can do a lot of things here, just as long as you have something asymmetrical. If it's too crazy, then of course you will violate the continuity equation and he might explode at step 1. So maybe you should modify it so it's not entirely crazy. But that's an option for you. This was just the velocity. Say now I want to have a look at the vorticity. I mean, we had that last lecture here now. It was process minus list, wasn't it? So yeah, here we had a whole bunch of options, and yeah, we have vorticity. What do you know? So let's just write post-process minus func vorticity. So now I don't specify any result folders. He should then take all of them and create a vorticity field. And let's see if that one worked. Paraform. And apply. And now we should have received a new variable, namely the vorticity. So let's have a look at that one. So this is the initial vorticity. So we have a tiny little plate here. Of course we will have something around that one. Maybe a little strange, but let's run that one and see. Yeah. So he will then show you maybe a little bit more of this vortex structure than just the velocity. So vorticity may be a good monitor for such a case like this. Okay. Question so far? That's okay? Yeah.
Will it affect the solution if you have the plate in the middle of the block mesh, so that the flow is able to hit the plate and then form a round flow, and then maybe trigger the vorticity earlier?
Yeah, will it change if you put the plate inside the domain instead of at the inlet? I don't really think so. I mean, imagine the flow is hitting a plate, and of course it's just going to divide up and down. It's quite robust there. So nothing happens before he hits the plate anyway. So I don't think it changes much, no. Try it and tell me. Yeah?
What is the utilization scheme that you use instead of the steady state to get this?
Oh, you mean this icofoam?
No, the DDT scheme.
Yeah.
For the instead of steady state, you use a different one.
Yeah.
What was that one?
So now we have, I mean, I switched from simple foam, which actually then should be a steady state, but capable of turbulent flow. I just choose the laminar. And now I switch to icofoam. That's a laminar transient solver. So he's built for that. So I can show you. Open, and then we go to the different schemes. So there you see the default scheme for time is Euler. This then is the forward Euler scheme, which actually is quite bad. It's a first order accurate, so you should have chosen something different. You have some options here. You have some options. Let's use the banana tricks and try to run that one. Icofoam. So, I've already run him, so he didn't want to start. Lazy one. Let's remove all these folders. That one. And then try to run him. Icofoam. So he crashes. Fatal. So he doesn't know what this is. Valid types. You have something called co-Euler, Crank-Nicholson, Euler, SLTS, backward, bounded, local order, steady state. So you have several options here. For the simple form, it's going to be this one, steady state. Then you use a delta T of 1, always. But here we have more options. Which one should we choose? Well, let's go back to the tips and tricks that we had earlier here. Where were we? Here we are. At the end of this tips and tricks, you find something about the transient solution. Here is also a word of warning. Remember the problem here. We send in a constant velocity, and then Mother Nature finds out that this is a transient problem. What about the time scale there? Well, we have no influence. Mother Nature decides. But we have to choose a delta T. So if you choose a very, very big time step and Mother Nature insists on this motion, you better describe it well, or else you're in trouble, of course. So you need a small enough time step, not just for the Courant number, but for the actual, say, physical frequency in the problem. So you better check this one out. The way to do it, simple. Simulate one with one time step, see what happens. Then you simulate again, but you take, say, your time step is 1/10 or 1/2 of what you had up here. Does your solution change? Okay, if it does, then maybe you have to even reduce your time step even further. And you can imagine if you're allowed here to take very, very big time steps, so you skip this frequency altogether, you're going to get a very, very wrong answer. So you have to play around with that delta t. So here, transient simulations, he quite fast, he goes to the pimple solver. The pimple solver, that's a transient solver as well, but it's also capable of turbulent flow. And to be frankly, this icofoam, it's a very primitive, simple user. This pimple foam setup has much more, say, possibilities. So, and also it's much more accurate. So we definitely should have used the pimple instead of icofoam. But never mind. But we have something in the delta t here. Here we are. So he just describes 3 of them, say the most widely used. Euler, very simple, first order, and normally it's fully explicit. So it's very easy to use, and it's actually quite fast. The numerics are not that hard. If you use a full backward step, Euler in reverse, you might say, that's fully implicit. But if it's, well, actually the backward here is, they have adjusted it, so it's second order actually. But when it's implicit, then the numerics become harder. You have to solve an equation system at every time step, in addition to whatever other numerical things you have to fight with. And then you have an option here, it's called Crank-Nicolson. Also second order, and also implicit. And yeah, you can choose between bounded and unbounded. It's also an option. So normally you will use the Crank-Nicolson with a blending factor. So here is sort of how many % do you want it to be implicit. If you choose that one to be 0, then it's actually the same as the first order forward Euler. If you choose it to be 1, it's a full backward. And if you use 0.5, as he recommends here, sort of you take the best of both worlds. Or as also he recommends, 0.7. Why not? So using a more advanced time scheme can actually be a good idea. So there you see these blending numbers between 0 and 1. You find these a lot in different schemes. So yes, that's also something that we can play around with. Yeah. And then of course we had some turbulence tricks here as well. Never mind. Let's go back to our problem here at hand. Let's see. Where were we? Here. Yeah, we can try Crank-Nicolson, why not? Crank-Nicolson, wasn't it like that? Nicolson 0.7. I think that's what was he recommended, and see if anything changes. Icofoam. I wrote it wrongly. Should be like that. Now then.
Still wrong, I think.
What?
Shouldn't be a D there, no D.
No, you're right. Let me try it like this then. What? What's wrong with that one? Crank Nicholson, Crank Nicholson.
No H. Yeah.
Ah, Nick. What country does this guy Nicholson come from? Nick. Now then. Thank you. I mean, he runs roughly just as fast. What's happened to my Quran number? Why has this one become so big? It was 0.7 or something last time. Let's have a look. Paraform. Apply, and then we look at the velocity here, and a little bit more violent. So definitely a good idea then to use a more advanced numerical scheme for the time derivative. Okay, let's let's end this setup here. Let's do something crazy here. What's this? 1 million or something? We try that one. We try that one. Get rid of all these result folders and try again. Well, he didn't crash, but the Reynolds number is now way too high. But Icoform, he sort of says, yes, I can still do it. My residuals are nice and small, so this one should be okay. Well, let's have a look. So here we have the velocity, and then we run. This is tending towards something chaotic. So a laminar solver should then have, as long as it's transient, yes, he will try to simulate a turbulent case, but he doesn't have any turbulence model. This one is going to be fairly unstable. For this case, it's not so complicated, but for another setup, it might explode. And you can do whatever you want here. Try finer and finer delta t, it doesn't help. It's still totally insane and totally chaotic and quite unphysical. So yes, we need a turbulence model to damp him down. If you wanted a good solution here, then you have to increase the number of cells enormously, and also you need a full three-dimensional setup to have it as a large eddy or a direct numerical simulation, and that is way beyond our scope. So what else can we do? Well, we should now switch from Icoform, and then as recommended, we should use pimple foam. How can you find a pimple foam setup? Well, let's have a look in the tutorials. I think we have it here somewhere. Open foam, tutorials, incompressible, and then we should have pimple foam. Under pimple foam, you find large eddy, RAS, and laminar setups. I will have a look into this RAS folder, and under that one you find several setups, and I found a cute easy one, Pitts Daily. Have you heard about that one before? Beautiful. I want that one, Pitts Daily. Now I don't want to copy that one into my own run folder because I have him already, so let's give him another name. Von Karman vortices pimple. Why not? Something like that. Now I just copy that one into my run folder, and no, I've copied in the wrong place. Yeah, I copied him inside that one. Oh, let's move him. Move this folder one step back, like that. Now he should be in my run folder. Let's see now, where are we? Yeah, he's there. So let's have a look at that setup. And it's a very, very easy and simple setup, so it should suit us well. But something here we have to look at. Let's see now. Gedit. We can start with the 0 files. This one we can overwrite directly. We have it already, so that shouldn't be a problem. I mean, this was this setup case for the PIDS daily case. I said 10 meters per second. We have one there, and we have different names for our boundary fields. So that one has to be overwritten. Same with the pressure. But you see here in the 0 folder, oh, this is a K epsilon case. So yeah, you have to edit all these files with the corresponding boundary names that we now have for this case. Furthermore, in the constant setup, now we also have the turbulence properties to worry about. Yes, we have to switch on a turbulence model, and here K epsilon, that's okay. Now have a look at the system folder here. The block mesh dict we can overwrite directly. We don't have really time to do all this, but let's see now. It's just one final thing I want to show you. Here in the control dict for pimple foam, you have one very, very nice thing here with the setup for a pimple foam. You specify as normal, find a delta T, a very small one, and then you have a right roll, everything, and then we have something down here. Adjust the time step. He can be set up to automatically change your delta T until you reach the maximum Courant number. Remember now, this one is an implicit scheme, so yeah, he can even handle Courant tal bigger than 1. I'm not sure I will recommend it. It might give you a solution, but if you are really interested in the time history, for that one to be correct, the maximum Courant number should be 1. But he can handle 5. He can handle 5. Let's just try this case for fun. What about this start delta T? Why is he so small? I mean, he should automatically adjust it, shouldn't he? Let's give him a challenge here. Start with a rather big delta T. Save that one. Then we try to run this case. Now I haven't changed it, so this is the PIDS daily case. Never mind that. We have the block mesh. Like that. No problem. Check mesh. Here. Okay. And then we run pimple foam. Yeah, he actually survived. Normally, when you're using this adjustment for the Courant number, the first step, you should be careful with that one. He might explode. Actually, he didn't here. Well, we can freeze him. He's going to take some time, I guess. Let's see now. The delta T is 0.000, and I started with 0.1. Of course, way too high. But you see, he still were able to handle it. And my Courant number, yeah, the maximum, well, I told him 5, so he's cheating a little bit, but never mind. So he's still able to handle it. But this can save you a lot of CPU times, of course. Yeah, let's just crash him there. We have some result folders, I guess. Parafoam. And apply. And if you look at the velocity here and play, yeah, he's getting towards the classical Pitts-Daly solution, the turbulent solution. Now for this problem, I have no objections that you choose a maximum Courant number bigger than 1. Here, obviously, we are interested in the steady state. So how you get there, we don't care. And if you get there as fast as possible, beautiful. Then that will be okay. But if you are going to answer a question, for instance, how many seconds does it take to start from 0 until you reach the steady state? Then you are going to need an accurate time history. Then your Courant number better be 1. Because here I think we can do some crazy stuff. Let's see now, remove all these folders starting with 0 dot something, like that. And then I specify maximum Courant number, 40. Let's see if he can take it. Yeah, he's running. And yeah, I'm actually a little bit above here. So I could use a much bigger time step. And okay, I have to admit, this is now not the correct time history at all in this fluid. But as long as I'm interested in just a steady state, okay. Yeah. Oh, now he runs into some problem. And then it was okay again. I guess I have a Windows machine, say no more. Let's just crash him. Yeah. Looks okay, I think. Or does it? No, he has exploded. Look at the delta T he's using now. Thank you very much. So that's one danger with using this pimple foam with an automatic delta T. Yeah, you risk stuff like this. And of course, this simulation could have gone forever, such a small time step. So you have to use it with care. Any questions? Yeah.
Is it relaxation factors that makes it possible to run for a Courant number larger than 1?
No, it's not the relaxation. It is the implicit schemes. An implicit scheme, say for a linear partial differential equation, is unconditionally stable. You can do whatever you want. You can take a time step of 1 year. You will get a solution, but the solution will be 4,000% wrong. So be my guest. It's still only so and so high order for the delta T, so a big time step, big output. Say no more. Okay, we stop here.